So last time we looked at, I gave you an introduction to what the whole lecture is all about, gave you some examples of learning tasks, and then how we specify them. You will have to catch up with the past videos there. I want to complete this now with giving you like 4 key elements of what machine learning is all about. And the first one is pretty straightforward. Also gives me an opportunity to repeat basically what you guys maybe have missed last time. So the first element of machine learning is that we need to somehow depart the real world and the real world objects for which we want to make a classification and go to the model world. And for that, there's the model formation function, alpha. It basically is a mapping of real-world objects into what we call a feature space. You have some kind of features, characteristics that explain or that characterize in a computer what the real-world object is all about. It could be an email, it could be a person, it could be anything, the real-world object. But you will have to decide what features to use, or you will have to have a mechanism to decide what features to use. And relating to these questions here, you will have to decide which features are probably most salient for your learning task. Your learning task is to somehow find a way from this part of the representation to map the represented objects to classes. And this mapping here, this function y that is to be learned, this should resemble as closely as possible, or approximate as closely as possible, ideally be identical to the real world function of some expert or some arcane mechanism of nature that actually maps the real world objects to their classes. So an email is mapped to spam or ham, and something like that. You can decide whether your emails are spam or not, but the machine has to learn that somehow. And you need to explain to the machine what it should look at in the feature space, map all emails always there, and then try to learn a function that captures your understanding whether you have a spam email or not. And that is, for example, just one classification task. There are a bazillion others. And then, of course, the usual question of the modeler then is, how much should I put into the feature space? How many features do I need? What do I need to count? What is relevant? What is not relevant? What is even confusing? And this is usually neglected in machine learning. We usually start with some kind of vector and feature vector, and the features come from somewhere. But this is where the real challenge lies in many cases, in many practical cases. Giving the machine learning algorithm the right knowledge of the real world objects and not overwhelming it with noise. For an expert, this is no problem. As an expert, you just look at your email and you see what's happening because you take in the email as a whole. For a computer program, you need to start counting words or something. So this is one of the first and most important parts, this model formation function. The learning algorithms that you saw last time, I will quickly pop them up again. This was at the end of the lecture last time, the LMS algorithm, which just skipping the formulas, which just uses a model function, any model function that you choose, evaluates it, calculates the distance of the calculated value of the model function to the wanted value, to the class value, and then comes up with a way of calculating the derivative of the loss, saying that which direction should the model function change, should the parameters of the model function change in order to be better, and then updating the model function. All of this here in formulas. Those of you who were there last time see this from the lecture there, and you have to relearn this, but it's pretty straightforward. as I said last time, all of the learning algorithms will be of the same structure. They always have these basic steps. We evaluate the model function that is to be learned, like the linear function here. We calculate the residual, the distance from the desired value C. We then calculate an update to the parameter vector of the model function, these W values here, this parameter vector, which is based on some optimization principle, and then we actually update the whole thing. That is all that happens in all algorithms. You can just click on these algorithms that we will see later in the lecture. They will all look similar and have the same steps following each other. And this can be characterized by what might be called the machine learning stack. So every machine learning problem works like this. We have data and a task to fulfill. It could be a classification task, like this. We have data collected, and this data represents this real-world function here, this expert classification of emails. This is our email, this is our class for the email. And we have lots of emails and lots of class attributions. For example, in a binary classification, we have only two classes, spam or not spam. Spam, not spam, encoded as numbers in this case. And this is our task, this is our data, and what we now need to formulate is a model function and thereby define a hypothesis space. With the LLMS algorithm, we defined a linear model function. A linear function in the parameters W with the features that we decided upon using the alpha function from before. This then is our hypothesis space, the p plus one dimensional space of all of the parameter vector of the linear function. And within this space, within all possible parameter values that we could possibly set here, which are real numbers, we have to search for the best parameter value that always computes the right number for every example. Can that be followed so far? Okay, good. So we have this space here, and we have a way of telling us whether we have done good or not with any given parameter function. What we do is we calculate the loss. First, the residual, which is the inner part here, the error that we are making. This is the delta of the LMS algorithm. And then the loss, which is the squared error. Why square? There are reasons for that. You could do different things. You can take different loss functions. But this is what we do here in this case for the LMS algorithm. And then we have the objective of minimizing that loss. We want to minimize the squared error that our model function makes when calculating a class for any given example object. If that error becomes minimal, or the square of the error becomes minimal, that means our model function closely approximates whatever is inside our data and however well our data represents the real world. We don't do regularization here. It's a different concept, but the LMS algorithm does not do it. And then, now that we can calculate the error and have a model function and have a way of representing our real world objects, the only thing that we need to do is decide in which way to go whenever we've changed the parameters. And we need, therefore, an optimization approach. And in the case of the LMS algorithm, it's the stochastic gradient descent. We take the derivative of the squared loss, of the derivative of the pointwise loss, and then go to its minimization. That's all. Basic analysis, only in higher dimensions. You will see all of this worked out as a worked math also on the slides later and also in the lecture, in the tutorial, I think. So this is the second most thing. All of these algorithms look the same. They all have these stacks with different realizations of these parameters, hyperparameters, as it were. And the questions that we have to ask and answer, similar to the alpha function before, is what are useful classes of model functions? Are linear functions always good? Should we choose something else? What kind of methods should we use to fit the model functions? How can we assess the goodness of fit? What effect has noise in our data? Because not all data are perfect. Humans who give us real-world judgments of emails make errors. Some just say, this is not spam to me, but to another person it's spam. And we need to live with this fact. So, and then the question is, what happens if our examples are not balanced? That means how we have much more positive examples than we have negative examples. For example, there was a time when 90% of all emails were spam, every day. Now, learn what is not spam. If you have only positive examples for spam, but not few negative ones. These days, it's 50% of all emails. The third interesting element of machine learning is what is our feature space constructed like? So the target image of the alpha function that we saw in the beginning. For linear model functions, we usually choose an inner product space. So a space like a Euclidean vector space where the dot product is defined. There are other kinds of inner product spaces, also called pre-Hilbert spaces for the mathematicians among you. And this enables algorithms like gradient descent or the support vector machine. But there are other kinds of spaces that we can consider. For example, probabilistic spaces or so-called sigma algebras. In probability, as you may recall, we have a sigma algebra based on the set omega, and the outcomes of all random experiments are part of this set. And the event space of a probability space is then the power set of omega, meaning omega is closed under complement, so for every event composed of outcomes, also the counter event composed of all other outcomes of the random experiments is part of the power set, and is also closed under countable unions, which is a bit more arcane math, where you just combine a certain set of events. For example, unify certain different events and then still find the complement of that in omega. So this enables probability spaces and enables statistical learning, for example, based on the naive Bayes algorithm. And the third feature space of interest that we will look at is finite set of vectors, nominal spaces. This is actually what we will talk about later today. There are other kinds of things that you can use as feature space. You can use graphs, you can use other things. There are many other ways of formulating and representing real-world objects in a computer, and these are perhaps the most common ones used. And the fourth element I want to talk about is how do we decide or classify between different classes. There's two basic approaches that are distinguished. This is the discriminative classification versus the generative classification. And I want to contrast them both here. Discriminative classifiers learn a boundary between classes. This boundary can be seen here. So if we have kind of positive and negative examples like here, and use a discriminative classifier, we want to find that boundary which maximizes the distance as much as possible to all positive and all negative examples. For a generative classifier, the situation looks different. Here, we rather think of the positive and the negative examples as drawn from two different distributions, probability distributions. And some examples are closer to the expectation of that probability distribution, others are further away. Same for the negative examples. And here, the question of classification becomes, if we choose this example, does it belong to this class or does it rather belong to this class? For the discriminative classification, the answer is clear. It's on this side of the boundary, therefore it belongs to this class. It's an assumption that we are making using this kind of classification. For the generative classification, we can now compute the probability of this probability distribution having generated such a case, or this one, and then choose accordingly. This is a different way of looking at things. And of course, a different way of classification, a different way of introducing bias into your classifier. And last, not least, so on the remark slide, all of this is set. Last, not least, especially if we look at generative classification, we will be forced to ask what kind of data do we learn from, or where do we get our knowledge from? Do we get our knowledge from the data, or do we get our knowledge from ourselves? So the frequentist versus the subjectivist paradigm of learning. With the frequentist paradigm, we believe that, or we assume that there's one unique mechanism that created our example data, the expert or something else. And we could take as an example, a simple example, coin flips. So we can use a coin and just flip it a couple of times and create data, and just record whether it's tails or heads. And now, if we consider that, all we have to choose now is a model function. For example, the binomial distribution, which models the coin flip. It's like a binary outcome. And then choose the parameter which maximizes the probability of seeing the data that we recorded. In the frequentist paradigm, we are looking at the data and asking what mechanism is the most likely one that could have created the data, or which parameter of the mechanism. And we therefore call this likelihood, not probability. This is a likelihood, and this is the maximum likelihood hypothesis. The hypothesis, as we learned from the past with the linear model function, is a parameter vector, the parameters of the linear model function. Here, for the binomial distributions, is the parameter theta. It could be also a different vector of multinomial distributions or something like that. So we can, this is a more general case here. And we are looking for that hypothesis, namely that parameter which makes this data most likely in the frequentist paradigm. It is a likelihood. As we are looking into the past, the experiment has already happened. We are not making a prediction of the future in that sense. And just as a notation thing, it's also explained on the remark slide, this is not a condition here. This is just a fixed parameter, and we are just looking for that parameter. So it's an exogenous variable in that sense. So in order to find the maximum likelihood theta for the model of the binomial distribution here, we just look for any parameter theta within 0, 1 that maximizes this likelihood of seeing the data. And we could use, for example, the expectation maximization algorithm for that. So we are just testing different thetas and choosing the one which is best. Basically searching for a theta in the hypothesis space of the range between 0 and 1. By comparison, the subjectivist paradigm. Here, we do not say that there is one mechanism that could have created the data, but there are alternative mechanisms. For example, with the coin flip, there's the person having given you the coin. And there might be someone who gave you an unfair coin, just to mess with you, or to get money from you. So the question is, what is our confidence in that person? And we can model that based on our prior beliefs. We look at the person and think, oh, it's a nice person. He will have given me a fair coin with 95% probability. But there's doubt, and so there's the alternative hypothesis that this person might have given us an unfair coin with 5% probability. This is what we call our prior, our knowledge of other people. And now the question is, what is true? So we have the data, and we can check. Given the data that we compiled using the coin we were given, we can now check which hypothesis is most likely given the heads and tails, sequence of heads and tails that we saw. So, is this one more likely? Has this one the higher likelihood? Or this one, given these two different alternative parameters? All we do is, again, basically maximize, choose the maximum a posteriori hypothesis in this case. So this is not the maximum likelihood hypothesis. It is the maximum a posterior hypothesis based on our two priors using Bayes' formula. So we compute the likelihood of the data having been generated with using the binomial distribution under this theta, for example, theta 1 or theta 2, multiply that with our prior of that actually having happened, and divide that by the likelihood of seeing the data in the first place. This can be simplified. So the binomial distribution is inserted, and this can be simplified by just removing the denominator, because we don't need it here. We just want to decide between the two alternatives. So maximizing the nominator is sufficient. So this will help us decide which is which, given the data. With this mechanism, we can bring our own knowledge to the table and add it to the data that we have recorded. So if we know better, if we have some really good knowledge that tells us something about the real world or gives us confidence one way or the other, we can bring this into the learning paradigm, for example, of the naive Bayes classifier. But we could also, of course, then use different kind of data or different kinds of experiments to estimate this prior. And this will then bring us squarely back to the frequentist paradigm. So we remove our own knowledge, but let the data speak. Which one is to be preferred? Depends on how much data you have. So if you have a lot of data, then let the data speak. If you have little data or no data at all, if you have little data, making prior assumptions is useful, for example, in medicine. If you have no data at all, for example, will the first flight to Mars, the first human flight to Mars succeed? You have only your knowledge and your experience. And that means there's only priors, and you can only choose among them. Once you assemble data, for example, once people flew to Mars and you see how many succeeded and how many failed, you can update your knowledge using that. So these are the basic elements of machine learning that we will be looking at throughout the lecture. Everything I've said here is also written here, so that you can learn later. This is this part. Questions?